In this example, I'd like to talk about a very special property of some special quadrilaterals. This is known as the Star Trek Lemma. So this is a quadrilateral for which three vertices lie on a circle. This is always possible. But the fourth vertex is at the center of the circle. So that's not always possible, to make sure that three vertices are on the circle and then the fourth is at the center. So this is a very special kind of quadrilateral that has this property. But the idea here is that this point O is at the center of our circle, which means that these side lengths BO and CO, those are both radii. So by definition, these must be congruent sides, right? The side lengths at least. But that's not the point of this Star Trek lemma. The lemma here states that the measure of this angle, interior angle, so this is the angle BAC, is half of the measure of this angle, BOC. This is an exterior angle, BOC. All right, and we'd like to prove that here. So we want to prove that the measure of angle BAC is equal to half of the measure of angle, this exterior angle BOC. Now that's not exactly how I stated it when I wrote it out here, and it's not exactly how we're going to prove it either. What we're going to do basically is move this 2 over to the other side. So we're going to show that this exterior angle has twice the measure of the interior angle here. Now, this is a very special case of the Star Trek lemma. So if you decide to go a Googling and you start looking up the Star Trek lemma, you might find some slightly different versions of this with some stronger hypotheses. So I just picked out a very special version that we can prove together. And so here's what we're going to do. We're going to look at this picture here and notice that if we are to connect, so since O is the center of the circle, if we are to connect A through O, then we automatically get a diameter. Okay, and so let's make this new point down here. We'll call this point, whoops, sorry, wrong tool. Let's call this point down here the point D. And once we've made this a diameter, so at this point, this line AO extended, right? So AD here is a diameter, right? So this is a diameter of our circle now. And in particular, what that means is the following. So I'm going to kind of cut this picture in half and only do half the proof. I'm going to leave half the proof for you guys. But now what I want to look at is let me get my colors straight. I want to look at the triangles that are made on the left-hand side of this. So AO and BO must be congruent to one another because these are both radii of the circle, right? So AO and BO, these are both radii. And so they must be congruent to one another. At this point, this is an isosceles triangle, right? So now we can say that since it has two congruent sides, that it's isosceles. And so this triangle AOB is isosceles. Isosceles. Okay? Now, what does that mean? Well, that means that this angle and this angle are congruent to one another. Okay, so these two angles are congruent to one another. And furthermore, let's take a look at, so we should write that down, right? So at this point, this is angle OAB. So the measure of angle OAB is equal to the measure of OBA. All right, so those two angles are congruent to one another. Furthermore, because we made this line segment go straight through, so AD goes straight through O, then that means that the measures of these two angles, so DOB and BOA, those must be supplementary angles, right? So I'm going to write this over here now. And we'll put this all together in a table in a moment. But the measure of angle, what did I say? DOB. So I'll just write it in words. But angle DOB and angle BOA are supplementary. All right. And if we look at this angle DOB, this is one that we're really interested in because angle DOB is part of the angle BOC that we're worried about, right? And I said I'm going to cut this in half. And essentially what I'm going to do is I'm going to prove this theorem, this lemma, for the left-hand side of our picture, and then let you guys fill in the details on the right-hand side. It'll be exactly the same. Okay, it'll be exactly the same as what I did here. Just everything will be flipped over. But the key thing here is that now this is an angle that we're really interested in, right? So this angle, we want to now have a relationship between this angle and this one. This is our relationship that we're trying to say something about, right? So that interior angle and then the exterior one out here, which is actually a central angle of the circle. Okay, but since these are supplementary, we know some properties about triangles as well, right? So the angles, all the angles of a triangle add up to 180 degrees. And at the same time, all the angles in this straight line must add up to 180 degrees, right? And so what that means then is that this portion of this angle, since the triangle and the straight line both share the angle BOA, then this portion right here, this angle BOD or DOB, has to be equivalent to the sum of these two angles, right? And so now we can see how this is going to go. It's going to be beautiful, right? But the angles of a triangle, so let's just write this out in a couple steps here, right? So angle BOA plus angle OBA plus angle OAB. These are the angles of the triangle, okay? So OBA plus angle OAB. These all have to add up to 180 degrees. At the same time, angle DOB has to plus the angle BOA. Technically, I should be writing the measures of these angles, right? So the measures in degrees of these angles, these have to add up to 180 degrees. And so now we just compare. We've got these two statements that both have to equal the same thing. So we set them equal to each other, right? They have to equal the same thing. And when we do so, we see that they're both going to have an angle, measure of angle BOA in common. And so what we end up with here is, right, hence this angle DOB, the measure of angle DOB, must equal the sums of the measures. So the measure of angle OBA plus the measure of angle OAB. But at this point, we remember that OBA is congruent to OAB, right? And so we're almost done here with this half of the proof, because this is just the sum of OAB, because they're congruent, right, plus the measure of itself again, and here we get our result. This is now 2 times the measure of angle OAB. All right, and so we've done, this is pretty much the setup for the proof, but the proof is now we've got that this angle right here is twice this one. So this angle, probably should open the other way, positive math direction, is the same as this angle. All right, and then you just repeat the argument with the other half of this picture. So the diameter you can still use, but you just use the point C and repeat the argument altogether here. All right, so let's try to write this up in a formal proof. All right, and then we'll be done. I'm going to leave the rest to you guys, but we'll be done with at least the left-hand side. All right, so here we go. So here's our proof. Remember, in this class we do just statements and reasons for our proof. So statement 1, I should label these statements and reasons. Statements and reasons. And so we've already worked out the whole proof, we just need to write it up. So statement 1 is that, so by the way, I've used technically OD, this entire line is an auxiliary line. This is a line that is not part of the actual picture that we were given. We threw it in there to help us do the proof. So we don't need to actually state that we're drawing the auxiliary line, but we are going to use that line. Okay, so what we can say then is that we just go in the same order that we did, right? So segment AO is congruent to BO because they're both radii, right? So AO is congruent to BO, and they are radii of a common circle. All right, and so then what we learn is that triangle AOB is isosceles. and this is because 2 has 2 congruent sides. All right, and then the next thing we said was since it's isosceles, then those 2 angles are, the measures of the angles are equivalent. So the 2 angles are congruent, right? So that's step 3 then. So this was angle, we are going to want to say something about OBA because OAB is the one we want, right? So OBA is congruent to angle OAB, and this is because this is basically definition of isosceles triangle, or we can call these congruent angles of an isosceles triangle. All right, now we have 2 more statements that we need to say. So angle DOB and angle BOA, these 2, so for the line segment, these 2 have to be supplementary. All right, and that's because of just properties of a straight line, but we should write it. So this was angle DOB and angle BOA are supplementary. And so this is, again, definition or identity. So definition of a straight line. Here I mean that the definition of a straight line is, or even you could say this is the definition of supplementary angles, right, that they form a straight line. But either way is okay. And at this point we can kind of just skip ahead here to say this one. So this is this right here happens to be the exterior angle of the triangle as well, right? So we can say by exterior angle of the triangle that this next statement is true. So we don't have to write everything. When you do the setup, sometimes you write more than you need. So we're just going to skip ahead. And probably I didn't even need to say step 4 here if I'm going to jump ahead and use the exterior angle property here. But again, this is angle DOB, and then it's going to be the sums of angles OAB and OBA. All right, so this is then angle DOB is, so in measure, right, the measure of this is equal to the measure of angle OBA plus the measure of angle BOA. No, that's not right, not BOA. It would be OAB. Right, OAB. Okay, and this is again by exterior angle of a triangle. And at this point, we can just use substitution from these previous properties, right? So OAB is congruent to BOA, and so 6 here is that the measure of angle DOB is equal to the measure of angle OAB plus the measure of angle OAB, which is the same as 2 times the measure of angle OAB. And this is substitution, right? Substitution from step 3, from number 3. All right, and so this gets us part of the way there. Now what I'm going to say, so this is the part that you guys are going to do. So I'm going to leave this for the interested student to complete. But the completion is to repeat all this for the right-hand side of the picture. Okay, this is just the right-hand side of the picture. And then draw your conclusion. So then we can conclude finally, once that's done, we can conclude the result that we wanted, which is that the angle in the quadrilateral, right, the angles in the quadrilateral are related. All right, and that's just by angle addition. So once you have the properties for these two, you just add those angles up, and they, you can eliminate the auxiliary line that we included in there. So our conclusion is then again that the measure of angle BOC, conclude that the measure of angle BOC is equal to twice the measure of angle BAC. All right, and that'll be the end of our proof once you guys fill in that right-hand side, but it'll be very similar to how we did it on the left-hand side. And so this is a nice picture. This is called the Star Trek Lemma. Like I said, some of you may have seen the show Star Trek, and this picture here looks a lot like the logo of the Star Trek fleet or whatever. I can't say that I watched a whole lot of Star Trek, but I do recognize the shape. So remember though that this lemma is not always true. So there were some hypotheses that we made. Number one, the most important thing, right, is that this vertex O is the center of the circle that passes through the other three vertices, and that is not a normal thing. So that's a very special property. Okay, but in this very special case, the Star Trek lemma holds, and the measure of this angle is half the measure of this one. Okay,